And now we move on to the very last part of our discussion on angular motion, wherein we take a look at a couple of more examples to round up our discussion on the topic. Consider now the following example. We have sample problem number 6. Starting from rest at the top of a hill, a solid sphere rolls downhill. The sphere has a mass of 1 kilogram and a radius of 0.5 meters. If the hill has a height of 8 meters, determine the linear speed of the sphere at the bottom of the hill. So the sphere has a mass of 1 kilogram, m is equal to 1 kilogram, and the radius r of 0.5 meters. The motion of the sphere starts from the top of the hill going down to the bottom of the hill. So initial case, top of the hill. Final case is bottom of the hill. At the top of the hill, the sphere is at rest, starting from rest. So initial speed is 0. Initial angular speed is 0. Initial case at the top of the hill, 8 meters above the bottom of the hill in terms of vertical height. Normally, again, when it comes to energy analysis, we typically set the bottom level, the lower level to 0 height. Bottom level is the final case, so final height is 0. We set it to 0 so that the initial height, the top of the hill, 8 meters above the bottom of the hill, the initial height will be positive 8 meters. Positive 8 meters since we set the final height to 0. The bottom of the sphere is, the bottom of the hill rather, is the final case. So the final speed happens at the bottom of the sphere of the hill. That's what we are looking for. The linear speed of the sphere at the bottom of the hill, that's the final speed. That's what we are looking for. Now the sphere is rolling. Whenever an object rolls, the axis of rotation passes through the center of the object. For a sphere with the axis of rotation passing through the center of the sphere, solid sphere, the moment of inertia is given by 2/5 mr squared. We know mass of the sphere, we know the radius of the sphere, thus we are able to calculate the moment of inertia of the sphere as it rolls down the hill. I is equal to 0.1 kilogram meter squared. Using energy analysis to solve this problem, to analyze and solve this problem, we have kinetic energy initial plus rotational kinetic energy initial plus gravitational potential energy initial plus external work done by external force plus work done by external torque, if any, is equal to kinetic energy final plus rotational kinetic energy final plus gravitational potential energy final. Initial speed is 0, therefore initial kinetic energy is 0. Initial angular speed is 0. So just like initial speed, initial angular speed is 0, initial rotational kinetic energy is 0. Initial gravitational potential energy is mgh initial. There are no external forces acting on the object that can affect the motion of the object. The same goes for torque. Therefore, work done by external torque is 0 and work external force rather is 0. Work done by external torque is also 0. Final kinetic energy is 1/2 mv final squared. We are looking for V final. Final rotational kinetic energy is 1/2 I omega final squared. And final height is 0. Therefore, final gravitational potential energy is 0. Now, the linear speed of a sphere as it rolls is basically the tangential speed of the sphere. And we know angular speed is just equal to tangential speed divided by radius r. So, final angular speed is just final tangential speed divided by r. So, squared. So, we have Vf squared over r squared. Isolating V final. So, we have V final. The final tangential speed is also the final linear speed. So, isolating Vf and plotting in the known values, we are able to calculate the final speed to be 10.583 meters per second. And lastly, we have sample problem number 7. A skater is spinning like a top. With her arms down, her moment of inertia is 1.9 kilogram meter squared, and she is spinning at a speed of 15 radians per second. She brings up her arms, which changes her moment of inertia to 3.8 kilogram meter squared. Determine her work done in bringing up her arms. Initial case, moment of inertia is 1.9 kilogram meter squared. So that's initial moment of inertia. I initial is equal to 1.9 kilogram meter squared. And her initial speed is 15 radians per second. The problem does not specify a specific direction for the motion of the object. So we can assume it to be either positive or negative direction. Assuming it to be positive direction, initial angular velocity is positive 15 radians per second squared. And when she brings up her arms, it changes her moment of inertia to a final value of 3.8 kilogram meter squared. So I final is 3.8 kilogram meter squared. Determine her work done, capital W, in bringing up her arms, in changing her moment of inertia from I initial to I final. Work done in this case changes not only the moment of inertia, but also we expect it to change the angular velocity, or in this case, angular speed of the object. In terms of work done, we are talking about change in the rotational kinetic energy of the system. So work done is equal to delta RKE, change in rotational kinetic energy. To be able to calculate the change in the rotational kinetic energy, we not only need the initial speed or initial velocity, we also need the final velocity. We can use conservation of angular momentum to determine the final speed or final velocity of the object. There's no external influence applied on the object, on the skater. So initial angular momentum, L initial is equal to final angular momentum is equal to L final. And L is just I omega, so L initial is I initial omega initial, and L final is I final omega final. Initial angular momentum is equal to final angular momentum. We know I initial, omega initial, and I final. We are able to calculate the omega final, the final angular velocity of the skater to be 7.5 radians per second. Knowing now the final velocity or the final speed of the skater, we are now able to determine the work done by the skater. Work done by the skater in changing her kinetic energy, RKE final minus RKE initial. RKE is just 1/2 I omega squared, so you have 1/2 I final omega final squared, RKE final, minus RKE initial, that's 1/2 I initial omega initial. And we know all the values completo. We are able to calculate the work done, negative 106.875 joules. And that's it for now. That's it for our discussion on the topic of angular motion. So thank you for watching.